Hi everyone. At the end of the last video, or at least the last video before the Python tutorial, I said what I was planning to do was to take those Gaussian wave packets I discussed in video 10 and start scattering them off different potentials. We'd look into tunneling, etc. We will do that, but before we do that, I'm going to step back a little bit. I had a number of interesting emails from students asking a number of pretty good questions, perceptive questions. And I just want to use this video to fill in some of the gaps perhaps in terms of the discussion of wave packets. And after this video, I'm going to leave you, or at the end of this video, I'm going to leave you with a bit of a conundrum. We'll leave you to think about that. And then in the next few videos, what I'm going to do is talk about measurement and observation and observables in quantum mechanics. That will get quite mathematical at times, but I'm going to take you through that hopefully quite slowly. Number of worked examples, number of simulations as well, and that will set us up nicely in terms of thinking about just how do we measure, what's the role of time evolution, what's the role of the time-dependent Schrödinger equation, and indeed the time-independent Schrödinger equation, and then we'll come back and we'll revisit wave packets then. But in terms of this video, what I want to do is actually spend a bit of time talking through one of the interactive figures I've set up. The rest of the other videos are going to be on the blackboard quite a bit, so if you'll excuse me, I'm going to sit by the computer and talk you through this interactive figure while I drink my, not quite iced tea, but cold tea at least. So I want to focus on this particular figure. And what we have at the moment is a Gaussian wave function. This is the real part. There's no imaginary part. There's no blue here. This is the modulus squared. So this removes any information as to phase, and also removes any information as to how much of the wave function is real or how much is imaginary. It just tells you about the magnitude of the complex number. Nothing about the phase. And here we have our Fourier transform, and that tells us about the waves that we need to build up this particular wave function in terms of their spatial frequency or wave number, whatever you want to call this. We've covered that before at length. Hopefully this won't come as a shock if I change the width of the real space in terms of the position representation of the wave function. Then it broadens out in terms of the Fourier transform, in terms of the representation, in terms of wave number or spatial frequency, or in particular momentum. So as I make the delta x smaller here, in terms of we can take our delta x as being, or the width of the Gaussian function here as being representative of our delta x. As our delta x becomes smaller, our delta k becomes wider. You know this. We've done this at length. So let me leave that round about there. So, okay, one of the questions on worksheet 3, question 1C, I believe, involves something called the shift theorem. And what that asks you to show is that if you shift a wave function along the x-axis, that it only affects the phase of the Fourier transform, in that we end up with a term e to the minus ik x0 times our original Fourier transform. So I'm going to do that here. I'm going to shift the wave function along the x-axis. Notice how nothing happens to the Fourier transform. And that's because shifting the function along the x-axis only affects the phase, and because we're plotting the modulus squared of the Fourier transform, we don't see any effect. Okay, let me set that back to 0 as I have. Now let's do the similar type of thing in terms of the Fourier transform, in terms of the k-axis. Now I'm going to vary this in a second, but first of all, before I vary that, notice at the moment, although I haven't put the numbers on the axis, apologies, at the moment this is actually centered on 0. This k0 is our mean value of spatial frequency, and our Gaussian representation, momentum representation of the wave function is centered at 0. That means we have equal numbers of waves with positive wave number and negative wave number. And if we think about what that means, it means that we've got equal numbers of waves that can travel in that direction and equal numbers of waves that can travel in the opposite direction. That means that what we end up with is no net momentum, and our wave function does not travel along in space. If, however, we now change the center or the mean spatial frequency, the mean wave number, look what happens to our wave function. I'm going to make this, I don't know, we'll make it 8. Say. By changing the value of k0, what we're actually doing is multiplying our Gaussian wave function by a plane wave e to the I k0x. That gives us a net momentum because p is equal to h bar k. So if we have a spatial frequency, if we have a wave number that isn't 0, it means we have a net momentum. It means our wave packet now has momentum. If k0 is positive, then it travels in the positive x direction. If k0 is negative, then it travels in the negative k direction. In the negative x direction. So let's just run this simulation and you'll see what I mean. So now you see that our wave function is traveling, our wave packet is traveling in space. That's because it's got a net momentum. Now if I change that net momentum, we'll stop the simulation, and if we make it minus 16, then hopefully you realize that it's now going to move in the opposite direction. Let's just check that, and indeed it does. And the speed at which it moves depends directly on the value of k0. So if we make k0 smaller, it moves more slowly. The other thing to realize is that as I increase the value of k0, the number of wiggles effectively in our wave function changes. I'm just increasing the width so you can see this better. So if I change the value of k0, then you see that the number of wiggles, if we want to put it like that, in the wave function changes. The spatial frequency is changing. And that's because what we are doing is we're taking our Gaussian wave function, which is purely real, multiplying it by e to the I k0x, which means we've got e to the I k0x is cosine k0x plus I sine k0x, so we've got real and imaginary components. And the higher the value of k0, the higher the spatial frequency, the more wiggles we have within our wave packet. So I'm just going to reduce the width again a little bit, and I am going to run the simulation, and I'm going to take auto scale off so you can see what happens. So it's moving, but as it's moving, it's also spreading out. And what you can also see here, in terms of the waves, this wave packet is almost breaking up. The waves are getting, if you want to put it like this, out of sync with each other. Spreading out because the different components, the different spatial components that make up this wave packet, the different spatial frequency components that make up this wave packet, travel at different rates. That's a subtle point. I'm not saying it isn't a subtle point. It's something called dispersion. Because the energy of our waves depends directly, the kinetic energy of the wave depends directly on the wave number, the spatial frequency. Then what happens is some waves are going to travel faster than others. So P is equal to h bar k. We also know we have the classical relationship between kinetic energy and momentum, which is E is equal to P squared over 2m. You should write this all down as I'm saying it. Therefore, E is equal to h bar squared k squared over 2m. There is no potential here. The wave packet is moving in free space. So there's zero potential. So this is all kinetic energy. So there's a direct relationship between energy, kinetic energy, and wave number. In fact, kinetic energy goes as the square of wave number. That means that those waves that have higher wave number, higher spatial frequency, travel faster than those who have lower wave number. That's exactly what you're seeing. Now, that is not a weird quantum mechanical effect. This is, again, like so much of quantum mechanics, an effect that's in wave physics. And we can see it anytime you've dropped a stone in a pond, you've actually seen, if you've looked at how those ripples spread, you've seen something very akin to this. I went down to the lake on campus at lunchtime, and I had fun chucking a few stones in the lake just to show you this effect in action in the big bad macroscopic world. So let me run this video, which I've played around with in terms of trying to enhance the contrast. So this is a few seconds after I've dropped the stone, and you can see these ripples moving outwards. Now notice at the edge here, we've got longer wavelength, and in here we've got shorter wavelength. The longer wavelength waves are traveling faster than the shorter wavelength waves. Now this is the reverse of what happens in the quantum mechanical situation, where the shorter wavelength waves, the higher spatial frequency, higher wave number waves travel faster. But it's the same idea. I'm not going to go into the physics of water waves. But it's exactly the same idea in that the energy, the velocity of the waves depends on the wave number. That's exactly what we're seeing. And that effect is called dispersion. If we go back to our quantum mechanical example, and let me widen this out a bit so you can see it and put auto scale back on, so it scales it a little better so you can see what's going on. As this moves, what's happening is that the higher spatial frequency waves, i.e. the shorter wavelength waves that comprise this wave packet, move faster than their lower spatial frequency counterparts. And so what you see is that the higher spatial frequency waves outrun their lower spatial frequency counterparts. Okay, I'm going to just move this, start that again and move it back. Let it run. So you can see this spreading out in time. And if I take the auto scale off again just to hammer this home, you can see that it's spreading out. The probability density is spreading out in space due to the fact that different spatial frequencies have different rates. So the packet is not quite literally, but is almost falling apart as it moves. It's spreading out. So there are two velocities here. There's what's called the group velocity, which is this little group of waves. And as that moves along, this is our group velocity. It's the rate at which this wave packet is moving together. It's the rate at which the group of waves are moving together. However, we also have something called the phase velocity, which is the rate at which the waves themselves that comprise that wave packet are moving. Those are two different things. Now, it's difficult to see that in the context of the Gaussian wave packet, but fortunately, we can move back to a much more straightforward example. It actually goes back to A-level physics, you'll be delighted to hear, rather than introducing some more new complicated stuff. And certainly you did this one from Newton to Einstein as well last year. You've encountered the idea of beat frequency before, where we take two waves which are very similar in frequency and we combine them, and what we end up with is a beat frequency. We end up with one wave modulating the other, so we end up with an envelope effectively. That's what you can see in this example. Now, we have just as we had with the Gaussian wave packet, we have a group velocity here and a phase velocity. So I've set the group velocity to 0 at the moment. So these wave packets, these groups of waves, you can see, which are modulated by this envelope. At the moment, the sort of mean position of each one of these groups, each one of these packets is staying fixed in space. But you can see the waves, if we follow just one of these through, it's moving through and it has a certain phase velocity. Let's change this so we can add a group velocity, just so you can see the difference between the phase velocity and the group velocity. Notice now how this is moving through. So the group velocity is actually at this point the same as the phase velocity. I've set the phase velocity to be 1. So the group velocity and the phase velocity are the same. So these little groups of waves are moving through at the same speed as which the wiggles effectively in the wave themselves are moving. Let's have the group velocity outpace the phase velocity though, to see what happens. Let's say make this 3. Notice now how these, if we try to follow the mean position of one of these groups, it's moving faster than the position at which the wiggles are moving. Now, it's a little bit difficult to see that, and you have to play around with this. The interactive video's online, so you can play around with it. That's with a positive group velocity. Now, you can hopefully imagine what's going to happen if I set a negative group velocity. Make it set it back to 0. And they stay fixed. The wave groups stay fixed in space. So that's the difference between a group velocity and a phase velocity. The best way to think of the phase velocity is how fast the wiggles are moving. And the group velocity is how fast those wave packets, those little groups of waves, move. What does that mean in the context of our Gaussian wave packet? Well, let's set this up so we've got quite a high group velocity, which would be our K0 here. This is going to control how fast the wave packet moves. And if we make this, if we make the width quite large, then what happens is we narrow down the range of spatial frequencies, the range of wave numbers we have, which means we've got a tighter grouping of those waves that comprise the wave packet. And therefore, we don't have the very higher spatial frequency components, so they're not going to dash off and outrun. So what's going to happen is that the dispersion of our wave packet is going to be slower. So let's try that. So it hangs together much better than if we have a narrow range. And also because it's also moving quite quickly, the group velocity compared to the phase velocity, it means that the individual waves comprising the wave packet aren't moving off at much higher rates, so the dispersion is much less. Let's change that. Let's reduce the width in space, which means we broaden out in terms of spatial frequency. Which means now you can see we've got these much higher spatial frequency, which means they're going to, and remember, the kinetic energy goes as the square of the wave number. So this is going to disperse much more quickly. He says hopefully. Yes, and indeed it does. You can see it's moving to the right here. It's moving in the positive x direction, and you can see, just as we saw, well, it's the opposite of what we saw with the water waves, but it's the same effect in terms of different waves with different wave number moving at different velocities. And you can see it spreading out. Okay, I did say at the end of the video I was going to leave you with a conundrum. We will come back to this a little bit further down the line, but it's good to ponder this for a little while, think about it. Some of you might have spotted this already, some of you might have been a little bit puzzled already, but the issue is this. I've said a gazillion times, broader in space, broader in terms of delta x. Let me turn auto scale on. Broader in terms of delta x, narrower in terms of delta k, and vice versa. And I can sweep this back and forth as much as I like and show you that. The issue, however, is this. I'm just going to turn auto scale off. I'm going to run the simulation again. We're going to let this wave packet disperse in space. It's going to spread out in space. You're going to see it spread out, so its delta x gets larger because those different waves, those different spatial frequency components have different energies, therefore different velocities, so it spreads out, it disperses in space. So our delta x is getting larger, and yet keep an eye on what happens to our delta k. Keep an eye on what happens to the modulus square of a Fourier transform, which is the momentum representation of our wave function. I've taken auto scale off so you can watch this. So this is normalized, so therefore its area remains 1. So if it's dropping in height, it's got to be spreading out, and I think you can see quite clearly it's spreading out. The dispersion is very, very clear here in terms of the waves, and yet our momentum, or delta k, the width of our Fourier transform, or momentum representation of our wave function, is rock solid, doesn't change, is absolutely unvarying. Question is how can that be? It's broadened in delta x. How can delta k stay fixed? Does this not break Fourier mathematics? Actually, does it not violate the Heisenberg uncertainty principle? What's going on? Is physics broken? I promise it's not my code. My code's working absolutely fine. Actually, this is exactly what should happen. And this is, not only is it not violating physics, it's actually, what you're seeing in action here is an incredibly important principle throughout physics, classical quantum, whatever, an incredibly important conservation principle. So ponder this. Why does it seem in this particular case that our delta x keeps getting larger and larger and larger, but our delta k stays exactly the same? Why is that, do you think? Okay, see you for the next video.